Welcome everyone to our channel Mathematics Parshala. This is a problem of CSIR NET September 2022 Mathematical Sciences. The question ID is 389. This is a problem of abstract algebra regarding class equation of a finite group. Let's see the question first. Which of the following are the class equations for a finite group? There are four options. So we have to check that which one will be a right class equation for a group of that order. So first look at option 2 and option 4 because these two options will be easier to examine. See, if G is a group of order, if for option 2, if G is a group of order 14, then what is the order of ZG? In option 2, given that order of ZG is 2 because 1 plus 1 is there, so it is 2. So now our G by ZG is a group of order 14 by 2, that is 7, so prime order, so G by ZG is cyclic and hence G is abelian. And for a abelian group, the class equation is only 1 plus 1 plus 1 for all such all are 1. 1 plus 1 plus 1 up to 14 times. So this is not the true class equation for a group of order 14. So option 2 is not correct option. Is not a correct option. Now see, look at option 4. For option 4, if G is a group of order 15, exactly in similar manner, now look at the order of the center of this group, order of ZG. It is given that 1 plus 1 plus 1, so 3. So our G by ZG is a group of order 15 by 3, that is 5, a prime number. So G by ZG is cyclic and hence G is abelian. So similarly the class equation will be 1 plus 1 plus 1 up to 1 15 times. So this is not the right class equation for a group of order 15. So this is not the correct option. In fact, there is a group of order P into Q like PQ prime and P does not divide Q minus 1. So for all such group of order P into Q where PQ prime and P does not divide Q minus 1, these groups are cyclic groups. So the class equation will be 1 plus 1 plus up to same time. So we can check this by this process also. Now look at option 1 and option 3. So see, for option 1 and option 1 and option 3, the groups are ordered 39 and 21. So they are the groups of order like this. They are the groups of order of G equal to P into Q, where PQ primes both are in this type and P divides Q minus 1. If P does not divide Q minus 1, then G is cyclic. There is a well-known standard result can be concluded from that Sylow's third theorem. So it will be easy to check that G will be cyclic. But here G is a group of order P into Q where PQ primes and P divides Q minus 1. For this it is also 3 into 13, 3 divides 13 minus 1, and here 3 into 7, 3 divides 7 minus 1. So now see, we can find the class equation of this type of groups. That will not be very difficult to find. Here we just say the rough sketch that how to find the class equation of the group of this type, and ultimately we write the classification of this type of groups and then examine that option 1 and option 3 are correct or not. See, actually in this group order of ZG must be 1, and so this will be singleton E. Why? Because if order of ZG is P or Q, then also there's that GYZG, that GYZG will be a group of prime order, so cyclic, and hence G will be abelian. So G is abelian, and the class equation will be 1 plus 1 plus 1 in that type, and so it is not the case. It is not the case because there our number of silo p subgroup, will be 1 because uh, our number of silo p subgroup np, that will be here 1. If G is abelian, then np will be 1 because that will be normal, so unique silo p subgroup. So there this p divides q minus 1 will not true. So actually there are if G is a group of order p into q, then two things may be happen, that one is p does not divide q minus 1 and one p divides q minus 1. So if p does not divide q minus 1, then the group will be cyclic, and if p divides q minus 1, then this group will be a non-abelian group. So in this case ZG must be singleton E. So now there are only elements of order p and q. There are no other element. So first see, the number of silo q subgroup nq is 1 plus qk, 1 plus qk, and here clearly this k must be 0 and nq is equal to 1. So unique silo q subgroup, and say H is that unique silo q subgroup, and order of H equal to here q. And see, there are q minus 1 elements of order q. So if A belongs to G be such that order of A equal to q, so there are such q minus 1 elements, and also for this type of elements which order is q, then centralizer of that element should be because A belongs to this centralizer, so this is a subgroup of G of order multiple of q, and this not equal to, if this is P into Q, then A belongs to ZG, so which is a contradiction because CA equal to G if and only if A belongs to ZG. So this centralizer must be a subgroup of order Q, and hence order of a orbit of A, the order of this orbit of A will be G index CA. G index CA, that is equal to PQ by Q, so this is P. So see, there are exactly q minus elements of order q, and each orbit of A contains p elements, and in this orbit there are only elements of order q. So such q minus 1 elements will be divided into these p orbits. So there are such, say, a1 a2 dot dot uh, dot dot uh, sorry, so we need how many orbit needs to cover all such elements of order q. So we need total q minus 1 elements by one orbit contains p elements, so by p, that is the total number of orbits, which contains the elements of order q. So So in this class equation, this P into Q equal to, for ZG it is 1 plus such orbits are there of order, each of order P, which contains the elements of order Q. So this will be like P plus dot dot P, and this will be Q minus 1 by P times. And now let me calculate the element of order P. So if we write NP, the number of silo P subgroup, this will be 1 plus P into say M, and since here P divides Q minus 1, so this Q minus 1 equal to P into say L. So Q equal to 1 plus P into L. So this NP, since this divides P into Q, actually this divides Q. So this will be actually equal to Q because Q is prime. So now there are Q number of silo P subgroups, say H1, H2 dot dot HQ. These are the silo P subgroups. So all such subgroups are of order P, and each subgroups contain P minus 1 elements of order P, and also this HI intersection HJ will be a subgroup of HI. So this must be equal to 1 or P. So if it is P, HI will be equal to HJ. So this must be 1. So for this, in this union H1 union H2 union dot dot HQ, there are each contain P minus 1, and there are no common element other than E. So there are total P minus 1 into Q number of elements of order P, and there are no other element of order P, because if there is any other element of order P, then if we generate the cyclic subgroup by that element, so that will be another silo P subgroup, because that subgroup will be of order P, and that will be any one of these. So since there are exactly Q number of silo P subgroups, so from these subgroups we have only the elements of order P. So there are total P minus 1 into Q number of elements of order P, and if we take one element B belongs to G such that order of B equal to P, then consider the centralizer of this element, that will be also, since B belongs to this, so that centralizer will be also a multiple of P, and for the similar reason we discussed above, for the centralizer of A it will be similar to, will be equal to P. So orbit of B contains PQ by P, so Q number of elements and each of order P. So there are total P minus 1 into Q number of elements of order P, and one orbit contains Q number of elements. So to contain all the elements of order P, we need P minus 1 into Q total number, and one orbit contains Q number of elements. So these are the total number of orbits which contain the elements of order P. So we have here, so the orbits Q plus all such orbit are of order Q, and there are such P minus 1 orbits. So these are the class equation. This is actually our order of G equal to order of ZG plus summation such orbit of AI I equal to 1 to up to Q minus 1 by P plus summation J equal to 1 to up to P minus 1 orbit of Bj, here A1 A2 A1 A2 AQ minus 1 by P are the distinct class representatives, such that each AI is of order, uh, each AI are of order Q, and also here B1, B2 dot dot B P minus 1 are the distinct class representatives for the elements of order P. So each element order of Bj are equal to order P. So this is the class equation for a group of order P into Q where P divides Q minus 1. So this is very clear because there are exactly two groups of order P into Q where PQ are primes. One is for P does not divide Q minus 1, that will be cyclic, and one will be P divides Q minus 1. So let me recall again here why ZG equal to singleton E. If ZG is not equal to singleton E, then G by ZG will be a group of order prime number. So G will be abelian, and for abelian group we have exactly one silo P subgroup and one silo Q subgroup, and we get the G will be cyclic. So this is not the case because here P divides Q minus 1, we get another group which is non-abelian and generated by two elements. So now this is the class equation. This is a very important result for any group of order P into Q where PQ primes and P divides Q minus 1. So we also said how this class equation came, the sketch of the proof, this, and now let us examine that for option 1 and option 3. So see for option 1, for option 1, for option 1 our for option 1 our 39 equal to 3 into 13. So our P equal to 3 and Q equal to 13. So we have this P plus P plus P. So it will be Q minus 1 by P times, that is 13 minus 1 by 3, that is 12 by 3, that is 4 times that P plus P plus P, and also P minus 1 times Q plus Q plus Q. So that is 3 minus 1 2 times. So the class equation should be 1 plus 4 times this P plus P plus P, that is 3 plus 3 plus 3. So 3 plus 3 plus 3 plus 3 4 times, and plus 2 times 13 plus 13. So and it is given there in option 1. So is a correct class equation. So this is exactly the class equation of a group of order 39 3 into 13. So option 1 is the correct option. Option 1 is the correct option, and exactly in similar manner see for option 3 21. So for 21 equal to 1 plus, so here it is 3 into 7. So our P is 3 and Q is 7. So P plus P plus P should be P minus 1 by Q minus 1 by P. This is yes, Q minus 1 by P. So this is 7 minus 1 by 3, that is 6 by 3, 2 times P plus P. So 3 plus 3, and P minus 1, that is 3 minus 1 times Q plus Q, 2 times. So 7 plus 7, and see this is also in option 3. So option 3 is also correct option, and this is the right class equation of a group of order 21. So it can happen. And also it can happen that if we take Z21, the class equation will be 1 plus 1 plus 1 21 times. But the question is which of the following are class equation for a finite group. So it can happen. So if we take a group of order 21 which is other than Z21, that is exactly one non-abelian group of order 21, then this will be the class equation of that group. And similarly, if we take Z39, the class equation will be 1 plus 1 plus 1 39 times. And if we take a group of order 39 other than Z39, so that will be one group which is non-abelian, and this will be the class equation of this group. So these are the correct class equation of a group of order 39, and for 3 a group of order 21. So option 1 and option 3 are the correct class equation for these two groups. So option 1 and option 3 are the correct options, and option 2 and option 4 cannot be the class equation of a group of order 14, and in option 4 a group of order 15. So this is the solution of this question. Okay.